All right, so recall last time we talked about the support of a quasi-coherent sheaf, um, and the associated primes. Now, what we discussed last time was taking a ring R and looking at the associated primes of a module inside the spec of the ring. And the thing I didn't quite have time to get to, so recall there are various characterizations of this set. I think sort of the best one for our purposes is that it's the primes where the vanishing set of the prime, which is the same as the closure of the prime, thought of as a point, is exactly the support of a single element of the module. All right, so that's something more general than just the support of either a sheaf or the module itself. This is the set of primes such that the image of M in the localization at this prime is not equal to 0. So you'll note all of these notions could be turned into algebraic geometry. We talked about all the different kind of ways of thinking about this set, but now I want to kind of geometrize them and think about, well, what if instead of having a ring and a module, and note here, we'll usually want to assume R Noetherian and M finitely generated. So there are natural sort of replacements for these in algebraic geometry. So now I'll want to consider X a locally Noetherian scheme. And F a coherent sheaf. X. And as we discussed last time, right, since R is Noetherian, I could have said M finitely generated, I could have said M finitely presented, I could have said M coherent. Those would have all meant the same thing because the ring is Noetherian. Just for whatever reason, for rings, we usually talk about being finitely generated. And similarly here, because X is locally Noetherian, I could have said coherent sheaf, I could have said finite type sheaf, I could have said finitely presented sheaf. Those would all mean the same thing. For whatever reason, we usually say coherent sheaf. Okay. So I can define the associated points in X of F by just saying, well, this is the union over all affine subschemes, open subsets, which are affine schemes of the associated points of the sections of F on U as a module over the sections of the structure sheaf on U. Right? So if I have an affine subscheme, it's spec of this ring of sections. And the sections of F are a module over this guy, which are finitely generated because F is coherent. So note if I take F and I restrict it to U, by the coherent hypothesis, this just means I take the sections of F on U, and I take, oh, I was using Twitter for this. I take the quasi-coherent sheaf associated. Okay, yes. Oh, I'm sorry, I should have said union. Yeah, sorry, union over all affine subschemes of think about this guy as a module, take its associated points as a module. Yeah. These are all, I mean, I'm just thinking about these as sets. This is a subset of the points of U, and I'm just taking the union of them. All right, and you can check for any affine subscheme. Taking the associated points of F and intersecting that with U exactly gives me the associated primes of this module. So this isn't, I don't think this is quite literally the affine communication lemma, but it's the same idea that you prove this is true when you have a distinguished affine open inside an affine guy. And then you say, anytime I have two affines inside X, well, I can cover their intersection with open affines which are distinguished in both. So this is exactly saying that if from the perspective of one affine subscheme, you look like an associated point. If you look at any other affine subscheme containing this guy, you will also look like an associated. So these are essentially the points that kind of control the sheaf. So one nice way to think about this is that if I take the sections of F on any open subset, let me call this V because I've been using U for an open affine. I want to emphasize that this is not necessarily affine. Then there's a map to take the product over the associated points in X of F, intersect them with V, take the stalks at these associated points. This map is injective. So in order to know what a section is, I only need to know what its value is at the associated points. Right, and this is sort of important because, so for example, if X is irreducible, as you'll show on your homework, it has a generic point. And in that case, the sections of X on any open U, any open that's non-empty, contains the generic point. So it injects into the stalk at the generic. Right, but if I have some coherent sheaf, well, maybe it's supported on one closed point, and it doesn't have anything interesting going on at the generic point. So the kind of thing you should think about here, right, as we've talked about spec of Z, right, which has all the individual finite primes, and then it has the generic point 0, right? And indeed, Z injects into Q, right? So the stalk here is Q. And any localization of Z will inject into Q. But I can have a coherent sheaf, like the coherent sheaf, where here I put Z mod PZ, and I put zeros everywhere else. Okay? So this is just the coherent sheaf that comes from the Z module Z mod PZ. And this guy isn't determined by its value at the generic point. It gets completely killed when I tensor with Q. Right? So I have to also remember the value at P. Or actually, I only need to remember the value at P. I don't need to remember the value at 0. And this is exactly that. If I take the associated primes to this sheaf, I get exactly the point P. Whereas here, if I took the associated primes of O of X, I would get 0. Right? Because the annihilator of any element of Z is 0. The annihilator of any non-zero element of Z is 0. The annihilator of any non-zero element here is the ideal generated by P. So those are in that case, the unique associated primes. And what if I had taken the direct sum of these two guys? Well, then both of these would be associated primes, and I would need to remember both of them. So this is sort of a generalization of the idea that if you have a abelian group, tensoring with Q remembers the torsion-free part. It's exactly the part that sort of corresponds to the associated prime 0. And then if you localize at the primes that appear as torsion, then you will also remember the torsion part. And in fact, one way to think about the associated primes is they're the smallest set where this is true. But if I don't include one of the associated primes, I'm going to mess this up. All right. So for example, right, we talked about this example last time of d of xy mod x squared y squared x, right? And the associated primes here were, so here's the spectrum. This is the prime generated by x. This is the prime generated by y. By that I mean this axis and this axis are the vanishing sets of the ideal generated by these guys. And then here, there's the vanishing set of x and y. And all of those are associated primes. And indeed, so what are the stalks at the corresponding points? So this is my back of this guy is my x. So if I look at O of x at the point ideal generated by x, what does that mean? That means I invert everything which is not in the ideal generated by x. So in particular, I invert y, and I invert any non-zero polynomial. So this ends up being exactly the rational functions in y. And this makes sense. If you think about sort of the set v of x, right? An open subset of this is remove finitely many points from the y-axis, right? So I'm going to get and for any rational function, well, I just remove all the points where the denominator vanishes, and that gives me a germ of a section. Similarly, if I take the stalk at the point given by y, then I get rational functions in. And similarly, if I look at this vanishing set where y vanishes, indeed, a function here which blows up at finitely many points is exactly a rational function in x. So there's a natural map of, let me call this ring R. There's a natural map of R into cy plus c of x. And this is not injective. because x times y goes to 0, right? This map is, I take an element of this ring. If I'm here, I kill x. If I'm here, I kill y. And I map in here. So x, y goes to 0. So I also need to include the local ring R localize at the maximal ideal x comma y. And then I won't, so x times y is a non-zero element of this local ring. I need all of these guys. All right, any questions? Maybe just since we've been talking about this, this is useful for allowing us to define rational functions. So what's a rational function on a scheme? So think about this example. If I wanted a rational function on the scheme, I would have to sort of tell you what happens on this guy and this guy. And I would also have to tell you what happens at the origin, because something sort of special is happening here. Oh, yeah. Yeah, exactly. Because if I didn't have this last term, x times y, which is a non-zero element of this ring, goes into here and is sent to 0. So, right, why did I include that? Right, why is x comma y an associated prime? It's because it's the annihilator of x times y as an element of the ring. Right, in geometric terms, if I sort of think about x times y as a function, well, it's 0 on here, it's 0 on here, but it's not 0 at the origin. So the origin is the support of this section of the structure sheet, which is just another way of saying like that the annihilator is this prime. The map is the obvious one, right? Like have a polynomial in xy, right? So the map here is set x to 0. The map here is set y to 0. And the map here is just the obvious map, which I believe is an injection. Yeah, that seems right. All right, I don't have a lot of time, so let me just sort of mention the definition here. Definition, a rational function on a scheme. So, right, a rational function on affine space is a function which is defined on an open subset, right? It's a function where I allow some polynomial in my denominator, so I have to remove the zeros of that polynomial. So the tricky thing here is, well, if I want a scheme, well, I know what a function is. It's a section of the structure sheet. So what's a rational function? Well, it should be a section of the structure sheet on an open set. But what kind of open set, right? Obviously, I would be doing the wrong thing here if I just took a function only on the x-axis and not on the y-axis, right? And the associated points is sort of one way of telling me what points do I have to remember. Is a section and O of x u, or u an open containing all associated points. So all the associated points of the structure sheaf. So these associated points are sort of a way of telling me what's generic and right. An open subset that sees the entire scheme has to contain all the associated points. Yeah, just open. Now, of course, right, this is a co-limit, right? So it wouldn't change anything if I said affine open. But usually, so any if I have a section on, I should say, modulo identification under restriction, right? So if I have a smaller open subset that still contains all the associated primes, I think of that as the same rational function if I restrict it. So if I want to say this in the fancy way, I'd say the co-limit of over all such opens under inclusion. But as usual, this is a filtered co-limit. If I take the intersection of two such opens, I get another such open. One interesting note about these guys, right? If I have two opens where it agrees on the restriction, then by the sheaf condition, I can glue. So there exists a maximal open, which is just the union of all opens on which it's defined. Right. So you're sort of familiar with this of like, oh, I can take a rational function and, oh, maybe there'll be something that cancels in the numerator and the denominator. Right. So maybe I defined it on an open set, but it's actually defined on a bigger one. Sheaf condition just kind of makes it obvious that this is going to work. If I have two opens, it agrees on the intersection, sheaf condition tells me I have a section on the whole thing. Yeah. Yes. I would call those functions or regular functions. So a regular function is a rational function. And this is contained in this bigger set of rational functions. And this is sort of generalizing the notion of fraction field. So if X equals spec R a domain, then the rational functions are just the fraction field. And there's only one associated prime, which is the generic point. So any non-empty open contains that associated prime. So if, or more generally, if X is integral, there's only one associated point. So rational function is just on non-empty open. So this is sort of, if my scheme is somehow worse, if it's not integral, how do I sort of fix this condition of being non-empty to mean big enough? One obvious thing you might guess is dense, and something that contains all the associated points is dense, but it's stronger because we can have embedded primes. So here, this condition says I have to have a well-defined value at the origin, because otherwise I will mess up this nilpotent stuff. Okay, cool. So that's taking care of all the stuff from associated primes. Any questions? Yeah. Integral, this means that O of xu is a domain for all u. And I believe you're supposed to be proving on your homework that this is equivalent to reduced and irreducible. So the irreducible tells me that I have a unique generic point, and the reduced part tells me that I don't have any embedded primes. Yeah. Yeah, right. That's the union of all the open sets on which the section is defined. All right. We'll come back to these later, but I have a more important thing in mind, which is, we're supposed to be doing category theory in this class. I mean, not all the time, but that's supposed to be kind of our context for thinking about things. So it's kind of bad that we haven't defined morphisms of schemes yet. And part of that is, well, we've had other stuff to worry about. And part of that is this notion is actually a tiny bit subtle. It's not really hard, but you have to be a little bit careful. So what kind of data would we need for a morphism of schemes? Well, a morphism of schemes it's a map, scheme is a topological space with this extra structure of the ring of functions. So obviously, given x, y schemes, well, obviously I'm going to need a continuous map from X thought of as a topological space to Y thought of as a topological space. Obviously, if that isn't part of the data of a morphism of schemes, obviously I've done something horribly wrong. Okay, I also have the structure sheaf on X and the structure sheaf on Y, and obviously I'm going to need some compatibility between those, right? It's worth thinking about the things that I definitely don't want to be morphisms of schemes. And for example, well, I have 2 points. Here I have C, here I have FP. There are no ring homomorphisms either direction from C to FP or from FP to C. Now, obviously, they're perfectly good continuous maps between the underlying topological spaces. So I need some extra data to rule this out. And obviously, that should be some compatibility between the structure sheaves. Okay. The easiest way to do this is a map of sheaves of rings from, well, how am I have 2 sheaves and they're on different spaces. So I need to compare them. The easy way to do that is to push forward the structure sheaf on X to Y, and then I can define a map from O of Y into here. So why does the map go this direction? It's because functions pull back, right? Another way to think about this is if Y is spec of B and X is spec of A, right? Then I want a homomorphism, morphism of schemes from X to Y if I have a map of rings from B to A. right? So in this case, if I take sections on here, I get B. If I take sections of the push forward on Y, and now you start seeing why I might enjoy this gamma notation. Maybe I'll actually switch to this one. So sections on Y of this push forward. Let me just to emphasize this notation, rewrite this guy. So here I have B. Well, by definition, the sections of this push forward on an open set are the sections on the pre-image. The pre-image of all of Y is all of X. So here I get sections on X of O of X. That's A. And so I want to map this way. So more generally, what I'm saying here is I want to map from sections on U, which is an open subset of Y, of O of Y, to map to sections of the push forward. So sections on C inverse of U of O of Y. And of course, I think about this as being like, oh, O of Y is maps of this set of sections should be like maps of U to some space, to some ring, for example, right? And then I would be pulling back by the map of phi inverse of U to U. All right, so this map is called pullback. Lockheed denotes it C sharp. All right. You write the open set in front. Pretty sure I remember that, right? Yeah, these are two different notations for the same thing. Right? So this is what I was saying last time. This notation is obviously dumb, but it's also the one that everyone uses. Right? And after using this for several years, people were like, this is moronic. This thing is a functor. When you have a functor, you write the name of the functor in the thing you're applying it to. But it was too late. We couldn't be saved. And now we have two competing notations, which you have to be aware of both. Here, here, here. Yeah. Yes. Yes. I was trying to compare it with the map between rings, right? So if Y is spec of B, right, that manifests by saying the global sections of O of Y is B. And if X is spec of A, that manifests by saying the global sections on X is A. So part of the data of this map of sheaves, if X and Y are affine, is this map, right? And I was trying to emphasize why you would have the map go this direction. Why doesn't it go the other direction since the map is from Y to X? And the answer is because maps on functions go the other way. I've kind of put off defining this. There's another way to write this, which is I could also write this as a map from the pullback of O of Y to O of X. This would be a map of sheaves on X. Now, unfortunately, I wrote this and I haven't actually defined what pullback of sheaves is, right? So this is a map of sheaves of rings. on Y. So since we've gotten to this point, we might as well do it. It's pretty important. So this pullback, now let's say of any sheaf, kind of the correct way to define it is exactly that sum of sheaves on Y of this pullback into G. Sorry, no, this is hum of sheaves on X is equal to hum of sheaves on Y from F to the push forward. So this is really kind of why we use pullback, is that it has this adjunction relationship with push forward. But you can also explicitly define it. You just have to be a little bit careful, right? So I'm going to look here. Here's my X. Here's an open subset of it. And I want to define what this pullback applied to U is. And the annoying thing is, well, somehow the map, right, the pre-image of an open set under a continuous map is continuous, but it's not true that the image of an open set under such a map is continuous. So what I have to do in order to define this properly is I have to look at all V and Y such that the pre-image of V, which is an open set, contains U. And I have to take a co-limit over these guys of F, V. So this is basically, I look at all the open sets. When I say co-limit here, I mean, again, this is a filtered co-limit. I'm taking, whenever I have two such V's, their intersection is also such a V, right? So this is basically, I look at smaller and smaller subsets, open subsets, that contain the image of U, which might not be open, and I'm taking essentially like a stalk construction, where if the image of U isn't open, I just take smaller and smaller opens around it, and I look at sections on smaller and smaller opens and identify them if they match under restriction. That's what co-limit means. Just look at smaller and smaller things and identify things if they match under restriction. Okay. So it might sort of actually look nicer, and you'll probably see some people define it using this pullback construction instead of push forward. And of course, we'll need this for things later. So I figured it was time to bite the bullet and define it. Okay, great. Okay. I have not written definition homomorphism of schemes. These are things we would want to include in the definition of homomorphism of schemes. So the thing I've written here is the notion of a morphism of ringed spaces. But this is not the full definition of a morphism of schemes. So this is a morphism of ringed spaces. But you can do a few examples to see it doesn't work very well to make this the notion of morphism between schemes. And the key thing is, right, a scheme isn't just a ringed space. It's a ringed space and it has affine opens. So I need to have some compatibility with the affine opens. And in particular, I know that a morphism between affine opens, I want to correspond to a homomorphism between rings. So somehow the morally correct definition of a morphism of schemes is one of those guys, a morphism of ring spaces, which locally looks like it comes from maps of rings between sections on open atoms. Okay, and this is one of these things where that definition can be made precise, but it's kind of a pain in the ass, right? To sort of say what it means to, cover your source and your target with affine opens and get everything to match up so that it looks like a morphism of rings. But let me show you first sort of the counterexample. So obviously there's a map of rings from Z to Q. Everybody knows this ring homomorphism. Might be the first non-trivial ring homomorphism you learn about. So what does this do on specs? So I want to map the other way, a map from spec of Q, which is one point corresponding to the ideal 0. And that maps to spec of Z. And what happens? Well, here I have all my individual primes. And then I have my generic point sitting over it. Well, the pre-image of the 0 ideal in Q is the 0 ideal here. So if I did the thing that corresponds to this ring homomorphism, I would send 0 to the generic point. And there aren't any other points of spec of Q. And the stalk here is Q, so I get the obvious identification. If I want to be very careful here, what happens when I push forward spec of this, the structure sheaf on here? So the structure sheaf on here, its sections on the unique point is Q. So if I take this push forward O of X, then I get it's just Q on all non-open subsets, non-empty open subsets. So it's the constant sheaf Q. And so my map from O of Y into here is, well, O of Y on an open set, this is a localization of Z. Right? My open subset is defined by throwing out some primes. I invert those primes. I get a localization of Z. And my map of schemes is just always, I map my localization of Z to Q. Okay, cool. But there's a perfectly good map of ring spaces that does something very dumb. I mean, this is the only ring homomorphism from Z to Q. So this should be the only map of schemes from spec of Q to spec of Z. But I could instead take the point 0 in spec of Q, and I could map it to some prime P. So that's a perfectly good continuous map of topological spaces. I'm sure you will all agree. So what's the push forward? The push forward I star of Q, U, let me actually say this a little more carefully on D of N. So I'm taking the integer N, I'm throwing out all the primes that don't, that divide N. So this is Q if I didn't throw out P, and 0 if I did throw out P. All right, and I have a map here from written O of, this is O of X. Here I'm going to have O of Y on D of N. Well, that's just take Z and localize it N. So maybe I'll, just to emphasize what's going on, I'll write Z adjoin 1 over N. So the map here is, well, if I have Q, I take the obvious map of Q adjoin 1 over N into Q. And if it's 0, I take the 0 map. It's the only choice I have. And that's a perfectly good morphism of ring spaces. But there are obviously very serious problems with it. One of which is, this isn't a coherent sheaf. We sort of see our problem immediately. I mean, actually, this isn't a coherent sheaf either, but this is somehow more badly not a coherent sheaf. Yeah, maybe a better way to say this is, so one of the reasons that pullback is nice is, what if I had done pullback here? The pullback of O of y is O of x. Whereas here, the pullback of O of y is the skyscraper sheaf that gives me the localization of z at the prime p. Something kind of weird happens here. Yeah, it's still okay. Anyways, I'll just emphasize this doesn't come from a ring on purpose, but that's really the bad thing about it. There are kind of other things that make you go, oh, this feels kind of icky. But the key thing is it doesn't come from a ring. And so what went wrong here? So what went wrong here, I'm almost out of time, is that there's an additional structure on schemes, which doesn't happen for arbitrary ring spaces, which is if I look at the stalk of the structure sheaf at a point, I get a local ring. And when I have ring homomorphisms between local rings, I often want to add an extra condition to them, which is that the pre-image of the maximal ideal goes to is the maximal ideal. A morphism of local rings. And here, I'm just to avoid confusion, I'm always using local ring in the commutative algebra sense. Some people call the stalks of the structure sheaf local rings. Is a ring homomorphism. So a local ring, right, is a ring and its unique maximal ideal. So it's a ring homomorphism from R to S, we call it C, such that, well, if I take the pre-image of N, that's going to be a prime ideal. The pre-image of a prime ideal is always prime, but the pre-image of a maximal ideal isn't necessarily maximal. So I'm adding an extra condition that the pre-image of this N isn't some smaller prime ideal, it's the maximal ideal. So the sort of problem here is that Z mapping to Q, well, it factors through a map of local rings where I localize at some prime. This is a map between local rings, but it's not a morphism of local rings. The maximal ideal in here has pre-image here, which is a smaller prime ideal. It's not the maximal ideal. So I'm out of time, so let me just write this up. A morphism of schemes from X to Y is a morphism of ring spaces comma, such that, so I always have an induced map from the stalk of, I'm going to call this, phi. So if I look at a point in X and I take its image in Y, the stalk at that point maps to the stalk of X at P, right? So if I have a germ of a section here, I pull that back. That's a section on open subset containing X. So it gives me an element of this local ring, such that this map is a morphism of local rings. So if I go to this example and I apply this construction for the point P equals 0, well, when it goes to the prime P, then the map I get, so this is my E sharp, the map I get, phi sharp, is the inclusion of this localization of Z into Q. And that's not a morphism of local rings. Yes. Sure, sure. Yeah, obviously it depends on P. Um, and you can think of this as the stalk of the pullback sheaf. So this is the map on stalks induced from the map, from the pullback to pullbacks. All right, cool. So that's what goes wrong in this example. And if we just add this requirement that the maximal ideals match up, which you can check always works out if you have a ring homomorphism, that's enough to sort of force everything to behave correctly. All right, that's all we have time for. So we'll talk more about this next time.